So this is G484 homework booklet question 2. 2A starts off with what's hopefully a fairly straightforward definition of conservation momentum. 2 marks, and I've separated the answers really out to 2 lines there. Key points: total momentum being conserved. There's no point in just talking about momentum being conserved, because you've got to demonstrate that you understand that it's not just about the momentum of the individual objects, but about the overall momentum. And for the second mark, this idea of a closed system or no external force. So those are the 2 marks there, fairly straightforwardly. And again, for inelastic collision, the key points there, but it's a loss of kinetic energy. Remember, we can't have a loss of energy. That would break the principle of conservation of energy, but a loss of kinetic energy. Moving on to part 3, it's a fairly straightforward momentum calculation. So we've got this head-on collision, and calculate the final speed afterwards. I hope you recognise it as a straightforward momentum issue. And so I've got the momentum of the large block to start with, adding on the momentum of the smaller block. I say adding on because that 2 meters per second is negative, so if I add that on, that becomes taking it away. That's the crucial thing with this part, really, is to spot that we've got that negative velocity, therefore the momentum of the 1.2 kilogram block is negative. Afterwards, I've got 3.6 times the total mass of 2.4 plus the 1.2. Total mass of this is going to be the 3.6 multiplied by that velocity. Of course, I've taken to the right to be positive. You could have taken to the left and it would just change the sign of everything. When you work that through, you simply get 1.33 meters per second. Got to show that that collision is inelastic, so to do that, realistically, I've got to work out the total momentum before and the total kinetic energy before and the total kinetic energy afterwards. What's interesting about kinetic energy is that we essentially lose the information about the direction because we square these velocities, and so strictly that should be minus 2 squared, but the velocities go. The other way of thinking about it is that when we're working out kinetic energy, it's speed squared, so I don't need the minus sign there. So just go back. You can see those 2 objects, 2.4 kilograms and 3 meters per second, 1.2 kilograms and 2 meters per second. So there we are, half mv squared for each of those, half mv squared for the 2.4 kilogram mass, half mv squared for the 1.2 kilogram mass. Add those up and they come to 13.2 joules. When I look at afterwards, I've simply got one mass, so I've got a half times the total mass times the 1.33 squared. I could do that treat them as 2 separate masses, both at 1.33. That would work fine. What you'll see is those 2 numbers aren't equal, and therefore it is an inelastic collision. That's taken us that far. Go into part B, where we're going to have a look at the helicopter. So we've got the blades of the helicopter. They're 5 meters length. We have done a practice question in one of the lessons that was very, very similar to this. The blades of the helicopter rotate in a circle of that radius. When the helicopter's hovering, the blades shoving the air down at 12 meters per second. Assume that the descending air occupies a uniform cylinder of radius 5 meters. It gives us a density. It asks us to show the mass of air propelled downwards in a time of 5 seconds. So if you imagine that cylinder of air being thrown down, the volume would be the cross-sectional area of the circle, pi r squared, which becomes the pi times 5 squared, times the length of the cylinder that's thrown down in 5 seconds. Well, if I'm throwing down 12 meters of air each second, and I do it for 5 seconds, I end up with that 12 times 5. That works out as 1500, 5 squared times 12 times 5. I've left that as 1500 times pi. No reason not to put that into a number. Just trying to see if I can actually see it in front of me here. it comes out as 6,126, give or take. No, that's a step further forward, sorry. I now need to multiply that volume by rho, by this 1.3, so simply mass is rho times volume. That gives me the 6,126. The advantage of leaving the pi in there, it's an intermediate step, so you wouldn't want a pi in a final answer to a question, but as an intermediate step, it just means we've avoided doing any rounding at all. And we're being asked to then calculate the momentum of that mass descending. That's a simple, the mass that you've just calculated times the velocity. Of course, you could have an arrow carried forward on that. Key question then is to being asked to calculate the force, and the idea, again, force is rate of change of momentum. So this is all Newton's law stuff. Newton's second law, force is rate of change of momentum. So I can have the momentum that we've given that air, the 73,500, rate of change, divide that by the time interval we've had, it's running for 5 seconds. That gives me a force downwards of 14,700. Then finally, it asks you to calculate the weight of the helicopter. And the point here simply is because it's hovering by Newton's, no, not by Newton's third law at all. By Newton's third law, the force on the air must be equal to the force on the helicopter, which we've used in part 2. And then the point is that it's in equilibrium. So the weight must be equal to this force, and of course weight is mg. So we get that the mass is that force divided by the 9.81, 1,500 kilograms. Obviously picking up any error carried forward on the way through there. So that's the end of G482 question 2.